All right, we're getting into our last lesson on two variable statistics. It's actually our last lesson on statistics in general. And like the others, there is a handout that goes with this one. It's really just a place to fill in blanks. But if you want to download that and make your note taking a little bit shorter and easier, please by all means do so. So today we're going to talk about correlation and causation. And I want to be really clear, there's really no math involved in this. This is just an interpretation of data and a general idea. And it is hugely important to understand the difference between these two things, because if you don't, you're like most people that work in corporations and make stupid conclusions and ridiculous things. This is, by the way, why things like, for instance, companies saying that smoking didn't cause cancer, it wasn't a problem, could last for as long as they did, is because people didn't understand the difference between correlations and causations. So the title slide here, the picture, we've got two kids here playing some unknown video game system that just happens to come with paddles. I'm guessing a Wii. Um, and the kid there saying, correlation does not imply causation. In this case, what they're getting at is that the correlation is that there is uh, a Wii remote in the television, and the boy is not holding his Wii remote. The girl is, so she has one. So there's probably the conclusion here is that the boy threw the remote. That would be the causation. So that the fact that there is a correlation, the fact that we see the remote in the TV does not actually prove that he's the one that put it there. It might strongly suggest it, and in many cases there is a causation with a correlation, but not always. And we can't make the assumption that there is, because there are several ways that the two can be misinterpreted. So when we have a relationship in data, so we plot our points on a graph and we see that there's a strong correlation, or maybe not a strong correlation, but let's assume there's a strong correlation. That doesn't mean that one of those things actually affects the other one, at least not in the way that we think it does. And maybe they don't affect each other at all. So there's a nice little cartoon down here that says, someday I want to get married because studies show that married people are happier. Married people are happier. That means you should get married so that you become happy. Whereas on the right-hand side, we have, I think that's Dilbert, saying a smarter interpretation is that no one wants to marry an unhappy person. So in this case, there is a correlation between marriage and happiness. The woman is assuming, and I'm not saying this to be sexist, I'm just pointing out the cartoon. The woman in the cartoon is saying that she believes that happiness is because of marriage. Happiness is caused by marriage. And what Dilbert's pointing out is that marriage is caused by happiness. Happy people want to get married. Angry, horrible, like bitter people do not. So there's two different interpretations of the same correlation. So let's go through a few different types of ways that data could actually be related if we see a correlation. The first type is called a cause and effect relationship. It's where it's pretty obvious what causes what. Um, and the problem with this is, just because it's obvious doesn't mean it's always correct. It could be backwards. So again, going back to the smoking example, for a long time people said, well, you can't prove that smoking causes cancer. Maybe people who have cancer or pre-cancer, the cancer causes an addiction to smoking. The cancer causes you to want to smoke. So maybe smoking is a side effect of cancer, not the other way around. And we now know that's not true. Many studies have been done both directions to see that that is not the case, that it is in fact the smoking causing the cancer. But a cause and effect relationship is usually one thing causes the other. In this case, again, I realize these are non-numerical things that we're not plotting data points for. It's just a conceptual thing. But here's a girl who tripped because her shoelace was untied. It's not that her shoelace is untied because she tripped, which I suppose is possible. But in this case, a direct cause and effect relationship means something happens because something else did. A more interesting one to think about, at least, is something called a reverse cause and effect relationship. And this is where that smoking thing comes in again. So it's where that it looks like a cause and effect, but the variables have possibly been reversed and interpreted in the reverse order. So as an example, If I did a study that showed that there was a strong correlation between the number of umbrellas that people were using and how much rain was falling from the sky, I could make the conclusion that holding an umbrella makes it rain. That's why there's more water falling from the sky, is because there's more umbrellas being held. I mean, that one's a pretty obvious, not true, but that could be an interpretation. Finding a correlation between two things doesn't prove what direction it is. So a reverse cause and effect relationship is just something that may have been interpreted backwards. And usually it's not as obvious as this one. It's something more like the smoking example. This one's actually a fairly common type. It's called a common cause factor. And it's where two things seem to have a correlation, despite the fact that they actually have nothing to do with each other. Um, what happens is that both of those two things, despite not being affected by each other, are both affected by the same third factor. So there's some other thing that's causing both of them to change, even though they have no interaction with each other. And a classic example of this is actually a strong correlation between the number or the amount of ice cream sales in a month and the number of shark attacks on humans. So someone who's looking at this could say, well, it's a cause and effect relationship. People eating ice cream causes them to be attacked by sharks. I don't know, that sounds pretty weak to me. Then you could do the other way around and say, no, 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 no. I think it's being attacked by sharks makes people want to eat ice cream. Okay, I'll be honest. If I was attacked by a shark, I probably would want to eat ice cream, but I always want to eat ice cream. Now, what's far more likely is that both of those are affected by a third factor, which is probably in this case temperature. This, by the way, is a true correlation. It's temperature that matters. As the temperatures get higher, more people are eating ice cream and more people go swimming at the beach. So both of those things go up. Has nothing to do with sharks knowing anything about the ice cream or the ice cream affecting sharks. Has everything to do with the third factor, which is temperature. The next one is called an accidental relationship. And it's where you've got basically two things that correlate to each other because they both have a similar pattern in what they're doing. So for instance, if I take a look at like bacteria in a petri dish, bacteria in a petri dish undergo exponential growth. My bank account also experiences, well, actually that's not true because I keep taking money out to buy stupid things. But if I left money in an investment, it would go up with exponential growth. That doesn't mean the bacteria and my money have anything to do with each other, um, but just means they're both going up at the same rate. Lots of things go up with exponential growth. So there's not necessarily a relationship at all. Um, anyway, I thought rather than come up with my own examples, I would steal some from Tyler Given, whose website tylergiven.com has I think it's called spurious correlations, and they're just funny correlations that he found, um, showing how two things are related. So here's a graph showing the correlation between the number of people who drowned by falling into a pool and the films Nicolas Cage appeared in. And you can see, okay, so we haven't seen graphs necessarily like this one before, where the left and the right side are actually different scales. So they're scaling differently, but that's okay. What it's overall, the overall idea here is that the shapes are similar. And if you actually did a formal regression method, or sorry, a formal correlation method in Excel, you'd see that it has an R value of 0.666. Actually, it should really describe the R squared value, but usually R values are just given. And whether it's positive or negative is irrelevant because it keeps going up and down all over the place. But there's like a 66.6% correlation between those two variables, despite the fact that I don't think people drowned in pools because Nicolas Cage was making films, and I don't think Nicolas Cage made films because people were drowning in pools. Maybe someday he will make one about it, probably because of this particular graph. It's another one here. Age of Miss America correlated with the murders by steam, hot vapors, and hot objects. I don't even know where people get this data from. But we can see that they do actually have similar shapes. Not perfect, but similar. Enough that the correlation, or R value, is 87%, or 0.87. So it is a strong correlation. I won't say whether it's positive or negative since it's nonlinear, but it is a strong correlation. And yet, I'm pretty sure they're completely not related to each other. And this one I thought was even more interesting. People who drowned after falling out of a fishing boat versus the marriage rate in Kentucky. Now, there is a possibility that people getting married in Kentucky makes them want to go fishing and fall off boats and die, but I doubt that that's the case. And I guess it's possible that people falling off fishing boats and dying could open up relationships to be possible in Kentucky. I don't know. But either way, there's a 95.24% correlation between these two things. And how they're related, I don't think there is a relationship here. I think it's just a coincidence that they both kind of did the same things over the same time frame, roughly. So that's an accidental relationship. By the way, I should point out before I go to the next slide that these kinds of graphs are often made based on a statistical method called p-hacking, and it's not a good statistical method. What it does is it just collects a whole lot of different data, and then it kind of just pairs them off randomly and measures their R squared or their R values to see which ones actually correlate and which ones don't. And that causes lots of accidental relationships. In fact, almost everything ever found with p-hacking is an accidental relationship. But it's often used to see if they can find, like a PhD student or somebody who's trying to commission a study, can find something to grab onto to try and see if there actually might be a correlation between things and why that might be the case. If you're interested more in p-hacking, just look it up. It's literally just the letter P, hacking. Okay, on to the next. Presumed relationships. A presumed relationship is something between a cause and effect and an accidental relationship. It's where it sounds like there could be a relationship between two things. Like you can fathom that it's possible, but you're really not sure how it matters or how it fits together. So these pictures here, there's actually a correlation between the number of senior women that did exercise classes and Arnold Schwarzenegger's popularity. So they kind of went up and down in similar fashion. And I don't know, was it a bunch of nice old ladies who saw Arnold Schwarzenegger, thought he was hot, and decided they were going to work out to look good for the Terminator? I don't know. I mean, I guess that's possible. I'm guessing it's an accidental relationship, but there could be something to it. This one I think is a little bit far-fetched, but there are more realistic examples. And usually they don't draw conclusions from noticing these correlations. They do additional studies to see if there actually might be something relating the two. So an interesting example, and this one actually has been verified since this time, but years ago, there was a noted correlation between Alzheimer's disease and aluminum buildup in the brain. And the question at the time was, do aluminum cans cause Alzheimer's? So, sorry, I said aluminum cans, I think. I think that because I drink too much Diet Coke and probably it will have Alzheimer's because of it. But does aluminum cause Alzheimer's? And the belief was, well, when they did autopsies on people that had Alzheimer's, they found aluminum buildup in the brain. So, oh, that's what's causing Alzheimer's. It's aluminum being there. Or does Alzheimer's cause the aluminum buildup? Alzheimer's is a disease. Disease cells do not function the same way as healthy cells. And because of that, maybe the modified cell shape or cell properties or whatever was actually attracting the aluminum and causing the aluminum to build up. So it was the other way around. Or are they both related to some third thing? Um, could it be, I don't know, there's some kind of food you're eating that causes Alzheimer's and it happens to come in aluminum cans? It's the food that's actually causing the problem, but you're also getting I don't know, maybe. Or is it just a complete coincidence? So these are all things where we don't know what the answer is. I think they did conclude that aluminum did not cause Alzheimer's. I don't know what the other thoughts on that were. But anyway, moving along. Another example is if you find somebody who's suffering from alcoholism and depression, is it the alcohol causing the depression or depression causing the person to want to drink? And the conclusion on this one is kind of both of them are spurring on the other one. So having one drives you towards the other one and then creates a vicious loop. But it is an interesting one to do. Is just because there's a correlation between them doesn't necessarily prove which one causes which. And that's why we're going to finish off here by reminding you that a correlation does not equal a causation. Knowing that two things are correlated doesn't prove one causes the other or vice versa. It just proves that there's a correlation. If you want to draw conclusions, do additional studies, and so on. Okay, we're going to call it a lesson, and actually I think we're going to call it a unit. We are officially done with statistics. The next time I see you in a video will likely be permutations, or at least that unit. So anyway, don't worry too much. There's some questions on the sheet here. I'm not going to worry about trying to say what the right and wrong answer is for each of them. For each of the examples, I want you to think about the different types of correlations that there are, the different things we talked about today, and see which one actually seems to fit the best. And if you could put forth an argument for each of them, I think you're okay. Anything I put on a test is going to be a pretty solid, obvious example of one of them. All right, until next time, we'll see you later.